We have observed that multipath fading channels exhibit multiple fades and possibly deep fades within a bandwidth of interest. And therefore we need to devise a modulation scheme that combats multipath fading and frequency selective fading channels, which is a subject we're going to get into, and we are going to get into the topic of orthogonal frequency division multiplex, or OFDM, to combat multipath fading channels. The original paper on OFDM was published in 1971. Data transmission by frequency division multiplexing using the discrete Fourier transform, and this was a big breakthrough, especially since the discrete Fourier transform could be implemented using a fast Fourier transform. Another very important paper is this paper published in 1989. In this paper, the cyclic prefix was introduced. The cyclic prefix allows for simple equalization using zero forcing in the frequency domain, since the cyclic prefix essentially gets rid of intersymbol interference that destroys orthogonality between the carriers in OFDM. So this was a very important paper in the development of OFDM. Here we show the diagram we had before for a multipath fading channel, in this case with 150 nanosecond delay spread. And as we noted before, within the bandwidth of interest, you have places where you have deep fades, and of course the spacing between these deep fades was related to the delay spread. If we had in fact a communication link, say a QPSK system with a carrier that happened to be located in this area here, then we would have quite a loss of signal to noise ratio and deterioration of performance, or actually loss of data. And rather than concentrate the data within a single channel, the solution would be, as we discussed before, is to break the channel into subchannels and transmit data within each subchannel separately. So we actually multiplex the data into these subchannels, and instead of supporting a high bit rate within one channel, we actually support lower bit rates within subchannels, and of course the aggregate of these subchannels supports a larger bit rate or throughput. Here we're showing a complex spectrum, 20 megahertz wide. Actually corresponds to the same bandwidth that is used in 802.11a. And we are going to discuss modulation in particular, and how we can take data and actually modulate it to these subchannels and then aggregate them and combat fading, and hopefully that will lead into an efficient modulation scheme called OFDM. To begin, we'll discuss the situation shown here as part of a review, and also this is very important in OFDM, and we will come back to this many times. What we show here is a pulse in the time domain, or you can think of it as a window in time domain, which has a width of t seconds. For now, let's let the amplitude be 1, and this being in a time domain. If we take the Fourier transform of this signal, then we get the frequency domain representation, which is shown here. And the frequency domain representation is also expressed by this expression here, which is a sinc function. The sinc function has the periodic zero crossings whenever this argument to the sign goes to 0, which happens to be multiples of 1 over t, the pulse width. So the first zero crossing we see is at 1 over t, 2 over t, 3 over t, etc. If we narrow this pulse, we make this pulse narrow in time, then of course 1 over t spreads out, which is typically what you would expect. If you have a narrow pulse, a high bandwidth pulse, then you expect the spectrum to spread out. And of course, if t increases, this spectrum would actually crunch in a little bit, as you can see by 1 over t. And in fact, in the limit, if this t went to infinity, you had DC, you just have an impulse over here. So we see the nice situation of course, between the time domain and frequency domain. And if you want to time limit something, or you're not limited in the frequency domain, if you limit something in the frequency domain, you become unbounded in the time domain. We sort of saw that situation with the Nyquist pulse shaping also. Here we have the expressions for the Fourier transforms, which we present here for review. X of f is the Fourier transform of the time domain signal x of t. Basically take the integration over minus infinity to infinity e to the minus j2 pi ft dt. And in fact, if we do have x of f, you can do the inverse Fourier transform and get back x of t from the frequency domain representation. So you have the forward Fourier transform and the reverse Fourier transform. And if you actually plug the time domain here into these equations, you would get the sinc function for the frequency response as shown here. This situation is going to come up in OFDM. This particular relationship is very important. We are going to deal with time windowed signals, and of course in the frequency domain we are going to deal with this sinc function. Let's go to the next slide. If we take the time domain window or pulse and multiply it times some complex number x of k, and then we modulate that with e to the j2 pi fkt, where fk is a frequency at index k, then we'll use the modulation property of the Fourier transform shown here. That is, if you take any time domain signal and modulate it by e to the j2 pi at, then the frequency domain just gets shifted by that modulation frequency a. And this is shown in the diagram over here, corresponding to the block diagram over here. So if we take x of k times this time window, we create a pulse, we modulate it, then if you go back to the previous slide, the pulse frequency response was the sinc function, and when you modulate it, it gets shifted in frequency and centered around fk. You still have the zero crossing at 1 over t, so the total width here is 2 over t, and the amplitude being x of k. So let's keep this situation in mind, because this is going to help us in combating multipath fading. Because if we can take a particular complex number which is data bearing and modulate that up to a subchannel, then we're sort of moving toward a solution. We would have multiple subchannels, multiple frequencies, carrier frequencies, f of k's, and we stack them by each other, and we can have these subchannels which combat fading in a multipath environment. So here we're actually showing that situation where we're using 4 carriers. The carriers are spaced apart by delta f. Now let's take a look at where we get delta f from. Here we're showing the time domain. So we have one window and it's modulated with a sine wave, and another window modulated by another sine wave at a different frequency, and so forth. We have 4 frequencies here. Now it turns out that these frequencies are selected so that their separation is delta f equals 1 over t. And what advantage does this give us? First of all, we'll notice that from the previous slide. Let's go back there. If we in fact window and then modulate, then the modulated frequency spectrum has a zero crossing at 1 over t. So let's take, for example, this particular pulse windowed sine wave. Its frequency response is this sinc function shown over here. The second modulated windowed pulse, as you see here, will have another frequency response, which is a sinc function. Now, if in fact the frequency difference between these two modulations is delta f equals 1 over t, then we'll notice that as this spectrum peaks, this sinc function peaks, this other sinc function from the adjacent channel, the adjacent subband, actually goes to 0. So there is 0 interference from the other carrier to the previous carrier. If we look at this windowed pulse, again the separation being delta f1 over t, then its sinc function goes to 0 when the previous carrier is maximum. Similarly, this subchannel goes to 0 when the next subchannel peaks. Same for the fourth windowed pulse, as you can see here. Therefore, we're achieving something very interesting here. We have the subchannels, each one carrying data independently. We're actually multiplexing the data in the frequency domain. They're separated by 1 over t, which happens to be a separation in which they have 0 interference with each other. And of course, in the time domain, that means that the window has to be also t. This is the preliminary work that's needed for OFDM. This is going to give us a situation where we can actually multiplex data, where the data is split between multiple subchannels, and the subchannels do not interfere with each other. And at the same time, we're very bandwidth efficient in the sense that each subchannel is pressed against each other in such a way that they don't interfere. If we did not use this sync function and, for example, use rectangular type frequency responses, then we would have to separate them by the width of the frequency response, and it wouldn't be as efficient as actually using these sync functions. Let's go to the next slide and see some of this in the time domain. Here we show the time domain representation of the pulse, and this time domain representation is actually the addition of these four window carriers, so to speak. We also see, and this is of course shown here, frequency response. The sampling rate here was 10 megahertz, so you actually see this is 5 megahertz wide, and we're actually occupying 4 subchannels, and you can see that the aggregate bandwidth is the width of 4 subchannels over here. By the way, the time is in microseconds over here. Now, one thing you would notice that in this type of situation is, since we're adding these tones, sometimes you have constructive and destructive addition of these tones, and that's sort of shown in the time domain over here. And this is something that will happen in OFDM, or when you use this kind of modulation, this kind of multiplexing in the frequency domain. And we see that there's a large peak to average ratio due to the constructive combination of some of the tones at certain phases, certain times. In fact, if we take 52 carriers and added them to each other, due to the central limit theorem, the addition of the 52 carriers approaches a Gaussian distribution. And here we're actually taking the data that you would obtain if you modulated 52 carriers, computed its variance and its mean value, and plotted the normal distribution that you would associate with a Gaussian distribution along with a histogram of the actual data, and we see that there's a very nice match to this. And this sort of is going to be important later on when we want to analyze the data, the actual time domain of the OFDM signal. So we're taking a multipath channel and breaking it into subchannels. Each subchannel would carry data, so we are actually multiplexing in the frequency domain, and we realize that if we use a time windowed signal, the pulse here, we would get a sync function in the frequency domain, which has a nice property that, first of all, if we modulate it, we just shift it up in frequency. And a couple of points we want to mention about this. Here we have a complex number, and this is a complex modulation. This spectrum here is actually not a single-sided spectrum, but is actually the spectrum, because the signal here is complex. If this was real, we would have a mirror image of it on the other side of this axis, but in fact this is complex and the spectrum is one-sided, as you can see. Now, as we mentioned, the idea is to take multiple carriers, space them apart, and multiplex them in the frequency domain, each one occupying a subchannel, and therefore combating the fading channel environment. We notice that the signal does have a little disadvantage in the sense that when you do this kind of thing with tones, you get a very large peak to average ratio, and the actual signal approaches a Gaussian type distribution, and this creates some issues in actual practical implementation in terms of RF power amplifiers and A to D requirements and so forth. We'll get into those later. The next slide is very important and sort of wraps up what we wanted to talk about in this section. We're basically showing how we would create these subchannels. We take the data, and recall that each one of these data is a point in the constellation, and every point in the constellation actually carries a certain number of bits. So we're taking the bits or information and multiplexing them into the frequency domain in terms of subchannels, and each complex number is modulated at a certain carrier frequency. The carrier frequencies are spaced apart by 1 over t, the width of this window function, pulse function here, and we add them all together and we get x of t, and x of t occupies the whole bandwidth of interest and combines all these subchannels. We pass that through the channel, and of course, you know, the channel could fade out, or we could have a deep fade at one of these subchannels, but the rest of the channels get through okay. And of course, from the demodulation part, we just basically demodulate each subchannel back down, and we filter it and recover the original complex number, which again can represent a point in a constellation, and then we map it back into the bits, and we get our original bit stream back. So this type of modulation, in which case the GT is actually a pulse, as we mentioned before, and the subchannels are actually sync functions in the frequency domain, is a characteristic of OFDM we're going to get into in the following sections. We want to actually come up with a very efficient way of implementation where we don't have to actually build parallel oscillators at different carrier frequencies, and we want to avoid all this complexity due to a certain number of mathematical relationships that exist when we actually do basically subchannel aggregation with sync functions. Here we want to get into the very important topic of showing how the subchannels that we mentioned, each representing a sync function, non-interfering with the other subchannels and aggregated to fill the whole channel as we have formulated so far, can actually be cast in terms of the discrete Fourier transform. And by doing that, we are going to simplify the implementation of OFDM, and this is one of the most important reasons why OFDM has become so popular. Here we again show the case where we have the complex numbers x0 through xn minus 1, and each one of them of course is windowed with a pulse with t, and modulated to a subchannel, and then they're added up and we get x of t at this point, function of time. If we express this in terms of the summation, we have x of t is equal to the sum from k equals 0 to n minus 1, the total number of carriers. Each carrier is a modulation of the x of k. So this is the actual formula for x of t. Now recall that x of k itself was a time-limited window function of duration t of a particular carrier, and each subcarrier in this case was a frequency which was a multiple of the carrier spacing. We show this right over here where we see the sync functions which represent the subchannels or subcarriers. Each subcarrier or subchannel was separated by delta f, which was the inverse of the duration t of the window time functions. Therefore we can represent f of k for the index k as equal to k times delta f, delta f being 1 over t, so we have that f of k is actually k over t. We'll substitute for f of k over here in terms of k over t, and we get the formula over here, which is the same expression for x of t, except we replaced the carriers with k over t. We still have the time index t. Now what we're going to do next is sample in the time domain this function x of t. So we're going to take x of t and sample it in the time domain with a sampling function. As we do this, we can manipulate the equations some more and get closer to the discrete Fourier transform formulation. In this figure we see that a time record of x of t, in this case we're simplifying it, just showing it as a sine wave, and we have actually sampled it in time at a sampling rate, for example f of s, and each sample is separated by the interval delta t. As we know, the duration is of course capital T, and if we have, for example, n points, then delta t is in fact equal to t, the total time, divided by the number of points, for example 64. So we have an expression for delta t. Each time would be Tn, which is expressed in terms of delta t times the index n, which is the actual position. So, for example, any point here, t sub n, would be n times the sample position times delta t. At each sample point, we have the actual value for x of n, which is a sampled version of x of t at that point. So that's what we have over here is x of n. So we replace t with n delta t, which is Tn, the sample time. So we have the previous expression, x of t, and of course t, and now we have it expressed in terms of a sampled waveform, x of n. Now if we look at this equation further, we can do one of two things. One is, let us express delta t in terms of t over n. So we'll replace delta t with t over n, and the t's cancel out. So we can cancel out the t's, and we're left with this expression over here, which I will highlight. So the sampled waveform is actually expressed in terms of the complex numbers x of k, and of course the e to the j 2 pi k little n over capital N. So let's focus on this expression a little bit. This is a very familiar expression to people who are acquainted with the discrete Fourier transform. In fact, over here we have a definition of the discrete Fourier transform. Typically, you have a series of samples in the time domain of a record of length n samples, capital N samples, and you can form what you call the discrete Fourier transform and obtain x of k complex numbers in terms of these samples. And this is the expression. You sum over n equals 0 to n minus 1, x of n e to the minus j 2 pi k n over n. So once you sum over n, you are left with only x of k, the index k. This is very similar to the Fourier transform. Now, just like in the case where for the Fourier transform you had the inverse of the Fourier transform, here we can, if we have the xk's or a record of n xk complex numbers, we can form the inverse discrete Fourier transform and obtain x of n from x of k. And this is the expression, mathematical expression for the inverse of the DFT. And if we take a good look at this expression over here, we see that it matches this expression that we obtained for the OFDM signal. That is the subchannels, each subchannel being separated by the other subchannels by the carrier spacing and so forth. So in fact, the signal that we represented before is the equivalent of the inverse DFT. What all this suggests, and this is one of the most important points, is that if in fact we modulate the signals, the actual constellation points, complex constellation points x of k, in order to occupy a channel which is divided into subchannels, each separated by delta f, and each being a sinc function, then we get the time domain samples x of n, which we transmit, of course, to the receiver. At the receiver, as shown over here, all we need to do is to perform a forward discrete Fourier transform. So we have the time domain samples, we perform a forward discrete Fourier transform, we get back the constellation points, the n constellation points, which we can then map back to the bits and recover the original bit stream. So what all this suggests is that orthogonal frequency division multiplex can actually be represented in terms of a modulator which performs an inverse DFT on n constellation points, capital N constellation points, and at the receiver we perform a discrete Fourier transform on the n received samples x of n to recover the n constellation points, complex constellation points x of k, which then are mapped back to the original bits, and we recover the original bit stream. So in this block diagram we summarize what we've derived so far. We have shown that OFDM can be formulated in terms of a inverse discrete Fourier transform in the modulator, and for demodulation we can use a forward discrete Fourier transform. So over here we show the constellation, and each carrier is a point in the constellation, x of k. We take the x of k's and collect n carriers. We perform an inverse DFT, and we get the signal in the time domain x of n. Over here we're showing the time sequence for the in-phase component, for example. We have n samples in the time domain. In the frequency domain we know that x of n exhibits the properties that we required in terms of carriers that are orthogonal to each other and are very bandwidth efficient. And the spacing between the carriers is such that we have flat fading over a multipath fading channel. Of course, provided that the carrier spacing was designed correctly. We'll get into that later. So this picture summarizes basically the OFDM modulation and demodulation. The modulation again is in terms of performing an inverse DFT on the carriers. Each carrier represents a symbol in the constellation. At the receiver, we perform a forward DFT on the time sequence. We recover the carriers, and each carrier represents a symbol in the constellation, which we can then map back to digital bits. Now this is very simplified, just a simple diagram illustrating the modulation and demodulation for OFDM in terms of the discrete Fourier transform. In this section, we are going to formulate the discrete Fourier transform in terms of a matrix formulation, which is very important for OFDM and actually setting up the block diagram representation of the OFDM modulator and demodulator. The matrix formulation has a number of advantages over the formula that you see over here. So the formula for the discrete Fourier transform is shown over here, where you have, of course, the samples in the time domain x of n, and of course the transformed complex samples x of k. What we are going to do is represent this in terms of a matrix operation. To do that, and this is another very important point about the matrix formulation, is that we get to see all n samples at once. So for example, we collect all the n samples x of n from x0, x1 through xn minus 1 into a vector that we denote with x underscore. So this vector actually collects all n samples of the time domain, the discrete time domain, and we collect all the complex samples, transform samples, x0 through x of n minus 1, also into a vector. This also is much better than the formula that you see here in terms of the summation, as we shall see. If in fact we represent x in terms of a vector and capital X in terms of the vector of course, complex constellation points in our case, then we can actually write this expression in terms of a matrix operation, where we have a n by n matrix of complex numbers that multiplies the vector x in order to obtain the transformed vector x0 through xn minus 1. The matrix is, of course, n by n, and each term here is actually the exponential here. So for example, if we look at x0, we substitute k equals 0 over here, then of course we have x0 times e to the j 2 pi k n with n0 and so forth. So actually this row times this column gives us the first term, and the same goes for like x1 and so forth. So you can actually quite easily verify that this matrix representation actually encapsulates this whole discrete Fourier transform formula. Each one of the w with superscripts k and n is shown over here in terms of the exponential, and you can actually verify that by substituting these exponentials into this matrix, and you will obtain, of course, the discrete Fourier transform representation. Now, what we will do is use the matrix W shown here in bold as the matrix shown here, and we obtain a very compact equation for the discrete Fourier transform. Shown over here, where we have x, vector x, capital X, is equal to W times vector lowercase x. So, to summarize, we have the discrete Fourier transform expressed in matrix terms, and in order to get the inverse discrete Fourier transform in matrix forms, all we need to do is, since W is actually a non-singular matrix, it can be inverted, so we can actually multiply by the left by the inverse of W, and we can obtain x, lowercase x, in terms of capital X. And in fact, it turns out that for this matrix, the inversion is actually the Hermitian transpose, and of course normalization of 1 over n. So we have two compact matrix equations for the discrete Fourier transform and for the inverse discrete Fourier transform. Very nice and compact, and to the right we've actually shown the expressions in terms of the summations, and they're all equivalent. Going back again, one of the benefits of the matrix formulation is that we actually show that the operations are in terms of operations on vectors. These are nice and pronounced. We will see the advantage of this formulation when we discussed the block diagram of the OFDM transmitter and OFDM demodulator. In the next slide, what we show is a table which compares the discrete Fourier transform with a fast Fourier transform in terms of reduction of complex multiplication operations. And this is very important in OFDM in this sense. The discrete Fourier transform requires on the order of n square complex multiplies in terms of complexity. And typically if n is large, that of course translates to a large number of complex multiplies, which makes it impractical to implement in hardware. However, the fast Fourier transform, which is mathematically equivalent to the discrete Fourier transform in infinite precision, can do the same operations as the discrete Fourier transform, but in n log base 2n complex multiplications. So instead of the DFT requiring n square complex multiplications, we only require n log 2 base 2n complex multiplication. So this table shows that for different values of n, how many complex multiplications are required for the discrete Fourier transform versus the fast Fourier transform. And of course, here we show the reduction factor in terms of the number of operations. So even if n is equal to 64, we require like 4,096 complex multiplies, but with an FFT only 384, a saving of by a factor of 10.7. And for n equals to 256, of course, we get a dramatic reduction in the number of complex multiply operations using an FFT, and also with n equals 1024. Now, these numbers for n are typically encountered in OFDM implementations in Wi-Fi, WiMAX, and other communications environments. The FFT is the subject of a different tutorial, and we are not going to spend much time on how it is derived from the DFT and how an FFT does in fact achieve the efficiencies. Suffice it to say that it's done by actually using a divided and conquer by 2, but we won't get into that. This table shows that in fact with the FFT, then the OFDM modulation is extremely efficient, as is the demodulation. As we discussed earlier, the demodulation involves a forward discrete Fourier transform or a forward FFT, and the modulation requires an inverse FFT. And as we can see from this table, the FFT being very efficient and actually implemented in ASIC or very efficient algorithms for DSP, this makes OFDM quite practical to implement. In the matrix formulation of the discrete Fourier transform, as we mentioned, it is very convenient. It is a very convenient formulation in terms of the fact that we represent the constellation points as complex numbers. We have n of them, which constitute a vector, capital X. We have n samples in the time domain, and this also illustrates the fact that both in the frequency in OFDM, both in the frequency domain and the time domain, we have the same number of samples, capital N, and we are going to investigate this a little further. So one advantage of the matrix formulation is it really highlights the fact that we are dealing with two vectors which have the same length. So we have the same number of samples in the time domain as we have in the frequency domain. And of course, this shows that we can transform between the two using the matrix formulation. In the following discussion on OFDM and sampling rates, we will use 802.11a as an example. In the case of 802.11a, the bandwidth and sampling rate are equal. But in 802.16a, or 802.16 2004, also in WiMAX, the sampling rate could be larger by a factor than the bandwidth. For example, by a factor of 8/7, actually using a separate formula that we'll get into when we talk about 802.16. But in our example over here, we are taking an example as 802.11a, so the bandwidth is equal to the sampling rate. But that is not necessarily the case, and we can have oversampling, where the sampling rate is larger than the bandwidth. Here we show this situation. Here in the time domain, we show a record of the n time domain samples x of n, and as you can see, each sample is separated by a time delta t, which is equal to t divided by n, capital T divided by n. And in the frequency domain, we have n carriers, just as like in the time domain we have n samples. In the frequency domain, we have n carriers, each representing a subchannel or a subcarrier. And the subcarriers are each separated by delta f, which is equal to, as we mentioned before, 1 over t. Now, if we are going to an OFDM occupy a bandwidth of, say, 20 megahertz, for example, then the sampling rate, in fact, is 20 megahertz, or fs is the bandwidth. This is what we want to highlight over here. If we go back and take a look at the time domain, then the sampling rate is equal to 1 over delta t. That's the definition of the sampling rate. So the sampling rate will be the inverse of the time interval between samples. Well, the time interval between samples is t over n, so the sampling rate, in fact, is equal to n over t. So that is, in fact, the sampling rate for OFDM, which is equal to the bandwidth. The carrier spacing, of course, is equal to the sampling rate divided by the number of points in the DFT, which is n, which it turns out that if we divide fs by n, we get 1 over t, which is actually inter-carrier spacing, or the spacing between the subcarriers, which is what we expected, which was to be 1 over t, the time interval. So now we've established the fact that the bandwidth that's occupied by OFDM, by the multiplex subcarriers, in fact, the bandwidth is the sampling rate, and the sampling rate is equal to n, the length of the vectors, as we mentioned before, divided by t, the total time interval in the time domain. In the next slide, we are going to actually investigate this with an example. In this slide, we will go over an example for OFDM using parameters from IEEE 802.11a. And one of the most important parameters actually determined by the FCC is the bandwidth that is used for OFDM. That is, for a particular transmission, the bandwidth is 20 megahertz. So each OFDM transmission can occupy a bandwidth of 20 megahertz. We're going to ignore at this point issues such as null carriers or guard intervals in the frequency domain. But if the bandwidth in fact is 20 megahertz, then from the previous slide we can draw the simple conclusion that the sampling rate is equal to 20 megahertz. It's that simple. So if the bandwidth for an OFDM system is given, then in fact the sampling rate is given. Here we show the spectrum, of course complex spectrum. Recall that in OFDM each subcarrier is a complex modulation, so it's actually one-sided spectrum. So the whole occupied bandwidth is a complex. And I want to highlight the fact that if we show the spectrum in OFDM, as shown over here, centered around, for example, DC, these two sides of the spectrum are not, and I emphasize, are not mirror images, because the spectrum is actually complex. This is not a real signal. We're talking about a complex spectrum. So these are not mirror images, and in fact every subcarrier shown here bears a particular data related to the complex point in the constellation. So for example, here we have a total bandwidth of 20 megahertz, for example. The whole band here is 20 megahertz, or fs equals 20 megahertz. We have actually n points. So for example, we're using 64 carriers. In fact, in 802.11a, n is equal to 64, and I'll discuss some of the implications of using 64 carriers. Some of those, of course, are null, but we won't get into that at this point. So the carrier spacing between subcarriers is delta f equals fs over n, or, as we mentioned before, it's 1 over t, where t is the time interval. So the thing we have is fs, and we have to determine what the carrier spacing is appropriate for this kind of communication system. Typically, the carrier spacing and defining the carrier spacing is driven by a number of issues. Of course, chief among them is to avoid frequency selective fading in each subchannel, as we mentioned before. So you do not want to have frequency selective fading within a subchannel. You typically want the subchannel to be narrow enough so that you have flat fading. You want to keep the FFT length reasonable, and you want to satisfy overall throughput, which puts a constraint on the minimum number of carriers that you are going to use. There are other factors that are involved in terms of robustness, carrier offset issues, and the data rates you're going to support. But if we let n equal 64 as in 802.11a, then the carrier spacing is simply delta f equals fs, the sampling rate, divided by n, or the bandwidth divided by n, which is 20 megahertz divided by 64, which turns out to be 312.5 kilohertz. So in this particular example for 802.11a, the carrier spacing is 312.5 kilohertz, as shown over here. Now, the carrier spacing determines the length in time, the actual window t, as shown over here, delta f equals 1 over t. So if we calculate t, which is 1 over the carrier spacing, then that's 1 over delta f, which turns out to be 1 over 312.5 kilohertz, which turns out to be 3.2 microseconds. So that is the actual time window, which is 3.2 microseconds. Now, the carrier spacing between carriers is also related to the delay spread. Again, we want to avoid frequency selective fading within each subcarrier. And that roughly translates to the fact that we can only tolerate delay spreads roughly between 1 and 2 microseconds. Delay spreads greater than 3, or for example, are not good for this choice of the value n. If in fact you have a situation where the delay spread is quite large, then you have to increase n, for example. Here we show the time domain, and in the time domain, the total length of the time record, or OFDM symbol, is equal to t, which turns out to be 3.2 microseconds. And of course, the interval between samples is delta t, which is 1 over fs, which is 50 nanoseconds, and this number will come up quite a bit in our discussions of OFDM. So in OFDM, in the time domain, the interval between each sample is 50 nanoseconds, which is just 1 over 20 megahertz. In this slide, we show the block diagram for the OFDM transmitter and the OFDM receiver based on all the discussions we've had before in terms of the formulation of OFDM, in terms of the inverse discrete Fourier transform as the modulator and the forward discrete Fourier transform as a demodulator, and of course the vector representation of the complex carriers and also the time domain. We will refer at this stage to this block diagram as the steady state OFDM model, since we are absolutely ignoring training and acquisition, which we will describe in detail when we present 802.11a. At this point, we are just interested in the actual end-to-end modeling and formulation of an OFDM transmitter and receiver. So going back, for example, to our QPSK type of modulator, we recall that if we used a single carrier for QPSK and sent that through a multi-path fading channel, the problem was that the carrier could be wiped out if it happened to be in an area where you had a deep fade, and it's not very good to operate with a single carrier in a frequency selective multipath fading channel. And we formulated the fact that we can use OFDM, in which we divide the channel into subchannels. Each subchannel then carries for example, a complex number, which is in fact represents the constellation. And in fact, if you do have deep fades, then of course you don't have a total loss of data. There are many issues that we will get involved in, because even if you do use OFDM and you do go through a fading channel and you have deep fades and carriers are in fact wiped out, we have to add some other mechanisms in order to still be able to recover the data without any loss at all. So we would have to discuss things like forward error correction and interleaving and so forth. Those are subjects that we will cover further on when we discuss in detail 802.11a. I'd like to point out that in this diagram, the oscillator shown over here actually has an in-phase component and a quadrature phase component. So here we output cosine 2 pi f c of t, and here we output sine of 2 pi f c of t, and we actually subtract from the in-phase term. And the demodulator, we also have a quadrature oscillator here where we have the cosine 2 pi f c t at the top and sine 2 pi f c t at the bottom leg. So basically the oscillator shows both the in-phase and quadrature phase terms. Also like to point out that in this diagram we are not showing the fact that we attach a cyclic prefix to the OFDM symbol before transmission and at the receiver discard the cyclic prefix before we do the forward FFT for demodulation. The cyclic prefix and its role in combating intersymbol interference and guaranteeing that the carriers are orthogonal prior to the equalization in the frequency domain using a zero forcing type equalization will be covered in a separate tutorial. So we refer to that tutorial for the details on that, but just assume that we are actually doing this and actually putting in a cyclic prefix and discarding it at the receiver in order to combat the intersymbol interference due to the multipath fading channel, and in this model we're ignoring that. So let's go back to our model. We actually have a data block that generates our 1-0 patterns. So it generates our actual digital data, hopefully scrambled. Just as in the case of QPSK, we collect every 2 bits and map them into a constellation point, and therefore we actually generate complex numbers x of k, which we can represent as the in-phase part and the quadrature phase part, and we can formulate them in a compact notation as a complex number. So the complex number x of k actually represents a point in the constellation. Each particular point in the constellation actually represents the bit pattern that have been encoded into that constellation point. Now here's where we deviate from QPSK, a single carrier type quadrature modulator. At this point, the QPSK mapper just outputs complex numbers x of k representing the particular points in the constellation. Here we group n of those complex samples together to form a vector, and that's why the matrix formulation of DFT was very important. So we actually collect these into a vector of complex samples, each representing points within the constellation, and each point of course carrying data. So we collect these in a vector, and then we go through this block, which is an endpoint inverse fast Fourier transform, which is the same as an endpoint inverse discrete Fourier transform. As you recall, that produces our time record, our time vector x0 through xn minus 1 of length n, which is our time domain OFDM symbol, which is the output of our inverse Fourier transform, the transformed complex constellation points. Here we go through a block which is referred to as a parallel to serial converter, which takes this vector and of course outputs them serially, so it'll output, like for example, x0, x1 through xn minus 1, but also separates them into the in-phase component and the quadrature phase component. We pass the in-phase and quadrature phase to a digital to analog converter to convert them to analog. We do some maybe interpolation filters, smooth things out, and we do a quadrature modulation in order to, of course, modulate the signal up to our carrier frequency, for example at 2.4 gigahertz or so forth. And of course now we have a real signal, not a complex signal. The modulated signal goes through a multipath environment. We have the noise added by the system, and the received signal is then demodulated. So let's go over here where we are going to discuss the demodulation process in OFDM. Again, this is a steady state model. We are ignoring all issues related to training and acquisition. So at the receiver we have a quadrature demodulator. So again we have a oscillator which is operating at the same frequency as the transmit oscillator. Now in 802.11 we actually have a carrier offset that we can tolerate between the two, which we will ignore for now and assume of course that both oscillators are operating at the same frequency. So we actually demodulate the in-phase component and the quadrature phase component. We pass them through a low-pass filter. As we discussed before, this gets rid of all the higher harmonics, the double frequencies, and only the baseband signal it remains, which is then sampled at the sampling rate fs that we discussed before. So, for example, fs can be 20 megahertz. So we sample both the in-phase and the quadrature phase terms. And once we sample, of course, recall that we are doing a low-pass filtering here, so there's no threat of aliasing. In an actual implementation of 802.11a, there is other issues that you have to worry about. For example, you will not typically sample at 20 megahertz, for example. You might sample at a higher sampling rate because you still need to worry about issues like adjacent channel and alternative channel and so forth. Those are issues that we will discuss later on. So once we sample the signal, it is still analog, and we will convert it from analog to digital. So now we have a digital sample for the in-phase term. We have a digital sample for the quadrature phase term. Collectively, these two terms represent our discrete time samples x of n, and I'm indicating a hat over here because these are approximations to the actual transmitted samples. So as we receive these samples, we collect n of them, so we have a serial to parallel converter to form our vector of time domain samples of length n. And once we collect all n samples, capital N samples, we perform a forward discrete Fourier transform, and in practical purposes we actually do a endpoint FFT, and we recover, as we discussed previously, our constellation points, our complex samples that represent our points on the constellation. And again, we are showing these with hats because they are, due to noise in the system and other impairments, they are approximations to the actual samples that were transmitted. And here I'm actually showing an equalizer block because we are going through a multipath channel, and the equalizer has to compensate for these fading or deep fades within the channel, and before we can actually map the constellation back to bits using the QPSK demapper. So this equalizer, we will discuss this in detail later on when we talk about acquisition, but we're just showing that you actually need to know this. So assume that you actually know what the multipath is and you actually equalize for the multipath effects before you actually take the constellation points and map them back into bits. So at this point we map the constellation points back to the bits and we recover our original data stream. So we've gone from a single carrier QPSK type modulator to an OFDM based QPSK modulator, and the QPSK basically being used to represent the bits in terms of the constellation, which is a QPSK type constellation, but the actual modulation is OFDM using the inverse FFT and of course the forward FFT for demodulation.